Right. Okay. This is session 2AP, and we have Mark Rader from IBM to talk about DB212 for ZOS and asynchronous system managed structured duplexing. Uh, any questions, please type them into the chat, and don't forget your feedback on session 2AP. I'd like to hand it over to Mark. Thank you.
Thank you very much, Marcus. And I'm going to make sure that my PowerPoint is responding. And since you've already read the title, I won't read it again. I would love to be doing this live and in person so people could ask questions as we go along, but it gets hard for me to read the chat as I present. So I'll just hold the questions to the end, unfortunately. Please remember to support the charities. For today's agenda, we're going to start by talking about data sharing and coupling facility structure duplexing in a general way. Then we'll compare system-managed duplexing of the lock structure with asynchronous system-managed duplexing of the lock structure to describe the differences. And then we're going to spend probably the most interesting part of the session, I think, is about customer experiences. Briefly, parallel sysplex basics. There are multiple DB2 members in a data sharing group. So what we normally think of as a DB2 subsystem, we will call a member if it's part of a data sharing group. DB2 will use coupling facility structures for high-speed sharing of information about locks, various status conditions, and data, the data itself, that is tables and indexes that DB2 uses. I'm going to say that the IRLM allocates the lock structure and that the master address space allocates the SCA and that DBM1 allocates the various group buffer pools that have shared data. This isn't precisely true. DB2 uses an API to XES, which is part of the operating system, and XES communicates with the structure and returns a response, but that's way too hard to say every time, so I'll just say that IRLM talks to the lock structure, and so on. The lock structure and the SCA are required structures. And what I mean by that is that if DB2 cannot allocate them, or if DB2 is running and loses access to them and can't rebuild them, then DB2 fails. In the case of the lock structure, all the IRLMs are required to rebuild the lock structure, and all the DB2s, the DB2 master address spaces, are required to rebuild the SCA. This will have some impacts when we talk about some configurations and duplexing. The original parallel sysplex configuration from the mid-1990s looked something like this. At that time, it wasn't ZOS or ZOS, it was OS390. But there were fundamentally four systems, which I will call central electronic complexes, or CECs. And each one of these systems, which might have been a separate machine on the floor, could fail in this environment, and we would maintain availability to the data sharing group. We did this because the LPARs that are running production are on separate systems from the LPARs that have the coupling facilities. And we made sure that the lock and the SCA were on a separate footprint from the DB2s that were exploiting them. So again, the original configuration had four systems or four CECs. And then we would spread the group buffer pools across the two coupling facility LPARs. The idea there being that some of them would be really large and would fit on one, and some smaller ones would be on the other. And we'd spread it out to balance the load, both memory and CPU, of the coupling facilities. So we could tolerate the failure of any single CEC. If the CEC happened to be the CF with the lock and the SCA, the two DB2s, the two RLMs and the two master address spaces could rebuild those structures. And of course, if we lost either of the OS390 or ZOS LPARs, we would have to restart the affected DB2 to release retained locks. The next configuration was after IBM introduced the integrated coupling facility. So we take one of those coupling facilities and take its LPAR and put it inboard on a system where there is also or already a ZOS and DB2 exploiter. So now we have three systems or three CECs, and as long as we keep the lock and the SCA on the external coupling facility, we can still tolerate a failure of any single system. We're going to spread the group buffer pools, and at around the time that we introduced integrated coupling facilities, we also introduced duplexed group buffer pools. So this is user-managed duplexing, and the term user really means Db2. So Db2 is writing code to that XCS API to manage how the group buffer pools are allocated, and the primary would be on one of the coupling facility LPARs and the secondary on the other one, and we would balance where the primaries were based on the overall load between the ICF and the external coupling facility. So customers liked this so much, they said, how about we went from 4 footprints down to 3, let's go from 3 footprints down to 2. Can you please order me 2 systems, each has an integrated coupling facility. That's how I would like to run this. The issue now is that the lock and the SA are not isolated from the Db2 and the IRLM that are exploiting them. They're going to be on the same system with one of them. And what happens if you lose a KEK? Well, of course, it's standard data processing answer number 1, it depends. You could lose just one member, or you could lose the whole data sharing group. Let's suppose that in both scenarios, we've put the lock and the SCA on KEK1 on the left, and we lose KEK2. Well, in that case, we lose Db2B, and we'll need to restart it to release retained locks, but Db2A can keep running. On the other hand, if the lock and the SCA are on ICF1 and we lose KEK1, then we've lost both an exploiter, Db2A, as well as a structure. And Db2B and its IRLM cannot rebuild the SCA and the lock by themselves. In that case, we lose the entire data sharing group. So now we have an availability exposure. We often call this the double failure scenario. So in this sort of 2 KEK, 2 ICF configuration, we recommend duplexing the SCA and duplexing the lock structure. Now this sort of duplexing is called system managed duplexing. That's how we introduced it when it came out in the early 2000s. And the idea was that XCS would keep the contents of the SCAs and the contents of the lock structure in sync before the IRLM or the master address space gets the response back to any request. For the most of the rest of this presentation, I'm going to call this synchronous system managed duplexing because we now have another variety to discuss. But when this first came out, we just called this system managed duplexing. Now we still have user managed duplexing, right? We still have the group buffer pools, they haven't changed. But with synchronous system managed duplexing of the lock and the SCA, I can lose KEK1 or KEK2, and the Db2 data sharing group would stay up, right? If we lost KEK1, we have a complete lock structure and a complete SCA. Db2B has all the contents that it needs to keep running. Of course, we'll have to restart Db2A to release retained locks, and we can reverse that conversation if we lost KEK2. Now, the downside of doing this is that duplexing the lock structure is very expensive. It's expensive in terms of application performance, but it's even more noticeable in terms of the CPU cost of the host CPs that are running the ZOS in this, both all the CPs that are running ZOS in both of these environments. So that cost kept some customers from exploiting this. And so they would run at risk of losing a box and losing their whole data sharing group. Db2 version 12 introduced asynchronous coupling facility structure duplexing, then that mitigates the cost and performance impacts. I'm going to be calling this going forward asynchronous system managed duplexing, or asynchronous SMD, to contrast it from what was originally introduced. So let's step back and talk about system managed duplexing and what it does, and then we'll get into the synchronous and asynchronous versions of system managed duplexing. So first of all, we have coupling facility structure rebuild. This is a process by which the sysplex will take an existing structure, in this case structure 1 on the left, and will create a new structure, in this case structure 1 prime on the right, and fill it with the data, and then proceed to use the new structure instance. So that's rebuild. Simplex rebuild says we rebuild the structure and just use the new structure and get rid of the old structure. Duplex rebuild says we use both instances and we keep them in sync. Now when we're thinking about rebuild in general, there are two ways we can do a rebuild. One, we can have the user manage the rebuild. So normally when I say user, I'm talking DB2. Theoretically, you could write your own application to use the XES API and build structures, and some customers have done that. But for my purposes, I'll say DB2. And so there's going to be significant programming effort that DB2 has to make to manage the rebuild. And at least one of the DB2s has to be connected to the structure to rebuild it. Now, as far as getting the data from the old instance to the new instance, well, we can copy it, we can reconstruct it from what we have in storage, we can rebuild it from DASD and logs. This is what happens if we have group buffer pool recover pending situations, or we can just start fresh with an empty structure and start using it. Let's contrast that with system managed rebuild. This is a more general purpose rebuild. There's no development cost for DB2 or a user application because the system, XES and ZOS, manage the rebuild. It does all the work. It can rebuild the structure from one CF to another CF, even if there are no connectors. However, it has to have access to the old structure to do that. So let's take the combination of user managed and system managed rebuild, and whether it's simplex or duplex rebuild, and think about the use cases. In the upper left, user managed rebuild is great for planned configuration, right? I want to change my coupling facility allocation, so I move all the structures off of coupling facility 1 onto coupling facility 2. DB2 does that with the group buffer pools, right? That's fine. For failure recovery, if DB2 is managing 2 group buffer pools and we lose one of the CFs, DB2 just keeps using the other copy of the group buffer pool. So that's the user managed rebuild on top and the user managed duplex on the bottom. Other than customers who've written their own support for this, DB2 is the only ZOS subsystem that uses user managed duplexing. On the right-hand side, we have system managed rebuild. This is great for planned reconfiguration, but it's very little use for failure recovery because if we've lost one of the CFs, the system can't rebuild the structures there because it cannot access them. On the other hand, system managed duplex provides robust failure recovery because everything from the one instance of the structure is already available in the other instance on the other CF. So those are our basic use cases. So what we're talking about in going forward is the SCA and the lock structure in the system managed duplexing, so the lower right-hand quadrant. Now there are costs for maintaining synchronous system managed duplexing. Those costs depend on a number of factors. If we think about the kind of structures and the number of requests that may get duplexed, we see there's quite a difference. Cache structures that are being duplexed might be duplexed, say, 20% of the time. That would, if we were doing the 80-20 rule, right? We only really have to duplex the updates. So on an 80-20 rule, we would duplex 20%. So for a cache structure, it could be anywhere from 0 to 100%. List structures and lock structures, pretty much every message is an update, and so we have to duplex all of those messages or all of those requests. Now, the cost of managing the duplex for system managed duplexing varies depending on whether looking at the ZOS CPUs involved or the coupling facility CPUs or the links between ZOS and the coupling facilities. So for ZOS processors, the ones that we measure for software charging, for example, we're looking at something like 3 to 4 times the cost of managing system managed duplexing. For the CF engines that are running the CF requests out there in the CF LPAR, we're looking at 4 to 5 times difference. Now this plays into the 3 to 4 times difference we see in ZOS, but it also makes the CF LPARs busier. So potentially this kind of increase could change your CF capacity plan. And of course, your CF links, if you have enough links, the 6 to 8 times is probably not going to become a problem. If you're short on links, this could definitely become noticeable. So I have some examples here. So system managed duplexing the cache structure is not what DB2 does, right? So that would be other kinds of structures that would do that. System managed duplexing of the SCA, yes, DB2 does that. And of course, DB2 supports system managed duplexing the lock structure. And the cost is going to show up for the lock structure in the ZOS CPU time. That's where it's going to be most visible because it's going to have a direct impact on processor busy, direct impact on software charging. Now, the overall impact to the system is going to depend on the structures, request frequency, read-write ratios, all of these things that will vary from workload to workload and from customer to customer. Typically, where we're going to notice it the most is that the service time for request from ZOS to the coupling facility will be significantly increased. And this significant increase can be further magnified if the coupling facility in question is far away. So if you have a parallel sysplex that's in one computer room floor, not so noticeable. But if you start spreading the sysplex so that you have a system and a coupling facility in one location and another system and another coupling facility, say, several kilometers away, then all of the overhead is going to be magnified. There are additional effects that are going to be harder to predict. I mean, I can predict what your synchronous service time changes will be, but I cannot predict how that's going to affect queuing of other subsystems or applications, how it might affect contention between your applications, timeouts that they experience, or various impacts on the coupling facilities themselves, right? Because as the lock structures, for example, get busier and consume more of the CF processor, what's that going to do to other CF structures? Is there enough capacity that they don't notice it, or are they going to start having effects as well? So they have all of these secondary effects to consider. So let's talk through how synchronous system managed duplexing works in a pictorial fashion. I've used the generic terms exploiter and XCS, but for me, the exploiter is the IRLM, right? Because that's where it's painful. It's when the IRLM is making a request to the lock structure. So IRLM makes a request, XCS takes that request and splits it and sends it to both copies of the duplex lock structure. Those two structures then exchange ready to execute signals to say, okay, they've each gotten this thing and they're ready to do something about it. Then they exchange ready to commit signals. And the whole idea behind the ready to execute and ready to complete signals is to make sure that each one of them is doing the same thing, so each one of them will have the exact same information, right? It's duplexed. Once they've both agreed, then the responses come back to XCS. Now that XCS knows that the request has gone in and been handled by both structures, so it's in sync in both places, only then does XCS give the response back to the IRLM, and the IRLM can carry on. So the increased synchronous service time that XCS notices is going to be the sum, if you will. The increase is going to be the 3A and B and the 4A and B, and the fact that we might have to wait for 5B over a simplex request. The IRLM isn't doing anything while all of this happens, and then it gets the answer back, and then it passes the appropriate response back to the application. So all of this gets even worse if we have CF2 at some distance, right? Then whatever it takes, it's going to cost more. The rule of thumb is 10 microseconds per kilometer for round trip. So you see 3A and B, that's a round trip. 4A and B is a round trip. So we're already adding microseconds depending on how far away CF2 is. Okay, that's how it looks with synchronous system managed duplexing. So let's look at asynchronous system managed duplexing. All right, this is what's new with version 12 of DB2. And so the IRLM is going to make a request. XCS takes that request, sends it to the primary structure. The primary structure is going to add a sequence number to the request and send the response back. Now, On the lower left, I've put notes about the ways we think about sequence numbers. There's the sequence number for the request itself. Then there's the last sequence number that's been handled by the secondary. We'll get to that later. And then there's the last sequence number that the secondary completed that the primary actually knows about. So the primary is going to send back the response to the request with the sequence number for the request and the last sequence number that the primary knows the secondary has completed. So XCS can keep track of what's going on. But this response comes back very close to the amount of time it would come back in a simplex request. At that point, the response goes back to the IRLM. So the IRLM has not waited anywhere near as long to get the answer back to the application, and the application can continue on and process whatever it's doing next. Asynchronous to item 4, and the IRLM handing the response back to the application. Asynchronous to that process, the primary structure is going to mirror the commands that it just handled and send them to the secondary. The secondary is going to send back, yes, I received it. Oh, by the way, this is the last operation that I did, right? The LCOSN or LCOSN. So now the primary has a record of that. And then the secondary will then take those commands and execute them in the order that they've occurred, right? And that's what the sequence number for is, to make sure that all the commands that happen on the secondary happen in the same order that they happen on the primary. So pretty soon after this primary made its decision, the secondary will have the same information. But every so often, we're going to check. We're going to issue a query. XCS will go out to the secondary and say, where do you stand now? How are things going? And that's because there is a certain amount of time, especially if coupling facility 2 and the secondary structure are far away. Now, in a parallel sysplex data sharing kind of environment, we have multiple ZOS systems. And even though each one is finding out from the primary what's going on, the values for the operation sequence number, the last operation sequence number completed by the secondary, and last one the primary knows about, those values will be different across the ZOS systems as each of them receives messages, right? So they're keeping track, but the values are going to be slightly different across systems. And all of this excitement and all of this delay, less delay than the prior picture, but all of this delay would be magnified if the coupling facility 2, right, with the secondary structure is far away. Now, I want to give credit where credit is due. Frank Kine, who was with the ITSO organization writing red books for many years at Poughkeepsie and is now with Watson and Walker, suggested the terms I've been using, synchronous system managed duplexing and asynchronous system managed duplexing, to differentiate between what was introduced in 2001 and then called system managed duplexing. The phrase synchronous system managed duplexing has to do with the operation of the exploiter, or the IRLM in this case. The IRLM is not going to continue until XCS has synchronously updated both copies of the lock structure. Now, it's important to realize that the request itself from the ZOS CP to the lock structure may be a synchronous request or an asynchronous request. This will be based upon the heuristic algorithm that XCS uses to determine the response time from the CF and whether it's better for the host processor to be dispatched to do other work or to remain busy while the CF processes. So we have two different meanings of synchronous in this chart, right? Synchronous system managed duplexing means synchronous relative to the IRLM. And then the request in support of synchronous managed duplexing could be a synchronous request to the lock structure or an asynchronous request to the lock structure. So I'm going to call this synchronous SMD. And then the new capability, asynchronous system managed duplexing, which was introduced by XCS and ZOS, as well as Db2 and currently is only supported by the Db2 lock structure. Again, it's asynchronous duplexing relative to the IRLM. That is, the IRLM can continue processing, can hand the response back to the application before we're absolutely sure that the secondary copy of the lock structure has been updated. And again, the requests in support of asynchronous system-managed duplexing could be synchronous requests to the coupling facility or asynchronous requests to the coupling facility. So I'm going to call this shorthand asynchronous SMD. So if I am asynchronously duplexing to a secondary structure, every so often, we're going to have to make sure that a sync-up has occurred because there's going to be some lag. The picture I went through showed that there's going to be periods of time where there's a little delay between the information getting from the primary to the secondary. So to make sure that the secondary instant gets caught up, ZOS is keeping track of this. So each of the ZOS systems is going to maintain a secondary update recovery table or CERT to keep track of what's in the primary and what's on its way to the secondary. So, and then it can check off the ones once they've been there, right? Once it gets back an LCOSIN P that corresponds to that particular one, it can check off, say, yeah, I've got that one, I've got that one, I've got that one. If a sync-up is needed, that is in a failure scenario, a sysplex-wide coordinator would gather all of the information from all of these logs, right, these certs, and coordinate and figure out, okay, which items made it and which ones didn't. So when I say a recovery scenario, that means we've lost the primary, right? We've lost the primary, we're switching over to use the secondary. Which things did not make it to the secondary, right? And that's what the systems have to agree on. Now, the connectors, in my case, it's IRLM and DB2, may have to delay their requests until the sync up that we're talking about gets completed. And we may have to back out uncommitted transactions as a result. So this sync up is if we have a failure in the primary. And so failover from the one lock structure to the other is going to be a little bit slower in the async SMD scenario than it would have been in the sync SMD scenario. Because in the sync SMD scenario, both structure instances are identical. And in async SMD, the secondary structure instance is going to lag a little bit. So the failover is a little bit different. That's why we need the certs. And then as far as the, if the outage isn't to one of the structures, but it's to one of the systems, right? Or we've lost one of the structures and one of the systems, which would happen in a 2 ICF configuration, then we have a situation where we can't just reconstruct it ourselves. And now the connectors, IRLM and DB2, we're going to have to back out transactions that were in flight. So this seems like an awful lot of work, right? All of this blue stuff, this extra recovery, managing the certs, coordinating them, that's a lot of work. Is it really worth it? Well, the answer is yes, it is certainly worth it because we're doing this with very close to simplex service times. This chart compares the synchronous service time. Blue is simplex, that is no duplexing. Orange is synchronous SMD, and gray is asynchronous SMD. And you can see that the service time for async SMD is very close to simplex. When I say 15%, I'm imagining a scenario where my normal simplex service time for a lock request is 5 microseconds. And now I'm going to say that that lock request is instead something like 5.75 microseconds, right? 15% higher, which is far better than the orange bar, which shows what's going on with synchronous SMD. If we move this so that we're farther away, let's say 10 kilometers away, and we've added a whole bunch of latency to the secondary structure, we can see that the orange bar for synchronous SMD is much worse, right? So in the chart, down is good because we're comparing synchronous SMD in the orange with async SMD for gray. Now that's service time. Let's look at overhead or transaction throughput rate. So if we look at the internal throughput, blue being the standard, right? That was simplex, that's the best we can get. It goes down almost, well, over 9% in the case of synchronous SMD, but only about 3% in the case of async SMD. And that's true whether it's short distance or, in this example, long distance up to 10 kilometers. So again, if we're comparing the orange bar with the green bar, in this case, up is good because we're losing fewer transactions over time in our overall throughput rates. So it's worth doing all this work. Okay. Lock structure duplexing is therefore more practical in more situations. We have performance that's very similar to simplex operations, even at distance. We get robust failure recovery, although failure takes a little more work, but the system is doing the vast majority of that. And recovery is not necessarily transparent to the exploiter. Which exploiters need to participate? Well, today there's only one exploiter of lock structure duplexing, right? It's Db2 and its IRLM. And were it the case that the IRLM did not have record data, it would need it, but IRLM does have record data. So because it has record data, we think of the record lock entries or the modified lock list that we care about. Because we have record data in the structure, we need to make sure that both instances of the lock structure are identical before we can commit the related transactions. What does this mean? Because the lock structure has record data and Db2 is going to participate as an exploiter in recovery scenarios, Db2 will not write the log output buffer until Db2 knows that the corresponding lock information has been updated in the secondary structure. Right? So Db2 has to be aware. And if you remember that blue arrow with the query going out to the secondary instance, every so often, Db2 will instigate, basically Db2 will ask XES what's going on, and XES will generate that blue arrow to do a query to the secondary to make sure everything is caught up. Because when Db2 is ready to commit, it's going to check, is everything there? And if it is, fine, we're done. And if it's not, then we initiate a query. Okay, I'm going to pause very briefly to talk about requirements. You need to be at least at coupling facility 21, which is quite old. You need to be at least at Z13 GA2 or beyond, or Z13S, or Z14, or Z15. If you're on a Z14, you do need to be at driver 36, otherwise there are problems. You have to make sure that the Z13 also has that driver update. This came out with ZOS 2.2, which is quite old now. We're getting ready to come out with 2.5, so hopefully we have this. And the list of APARs are by no means all inclusive, right? These were minimum APARs for a starting position. You would definitely want to check to make sure that any additional APARs that are required are on your system. The other requirement is this bullet at the bottom. All systems in the sysplex must be capable of using async duplex protocols. So if you want to do this, all the connected systems have to be able to participate. So they all have to meet these requirements. There are a few changes with async system managed duplexing. If we look at the coupling facility usage summary, which is part of the RMF coupling facility activity report, we're going to see that in the structure summary or the usage summary, we're going to indicate that this structure is the secondary structure, and the A means that it's an async. It's in an async relationship. So that little red rectangle will look different in your reports. These red rectangles also look different. If it's the primary structure instance, we'll call it primary async. And then I've got the two values here, which we'll talk about in a second. And then below the bar, we're going to have the secondary structure, right? That red rectangle, which is slightly off center for some reason, indicates that's a secondary structure in an async relationship. And if you look at the data blocks, you're going to see significant difference. All of the lock requests are going to the primary. And they're getting, in this particular example, 4.6 microsecond service time for the synchronous request, which is, well, depending on your environment, that's really good. I've seen even better, but that's pretty good. And this was a report from early days. The red rectangles in the lower half of the secondary structure show far smaller numbers. Instead of over 83,000 requests per second, we're looking at 771 requests per second. And that's because these reflect those query requests where XES is going out to the secondary to find out where the secondary is. So the secondary is going to take longer to respond because it has to gather some information and send it back. So instead of 4.6 microsecond service time, we see 17 microsecond service time for these queries, but there's far fewer of them. In case you're reviewing this at night because you can't sleep, I just highlighted on this page the points that I just made on the prior page. There is another change with Async SMD. There's a new section in the RMF CF activity report, and this is called Async CF Duplexing Summary. You can see the white async somewhat highlighted. So I borrowed this screenshot from a piece of customer data. So I overlaid their structure name to protect their name and just called it prodlock1. But you can see that there's information about async CF duplexing operations and sync up requests. So the block just to the left of center is request to the primary, and the block to the right of center is the duplex sync up request. And you can see there are far fewer of them. Okay, that's the nuts and bolts. Let's talk about customer experiences. So I've got several to describe. One is a European bank, a very early experience with synchronous system managed duplexing, and when async was available, they went there. A North American bank who had chosen not to do synchronous system managed duplexing, so they were doing simplex, and then when async was available, they went that route. And then the third example I have is a North American financial institution that was using synchronous SMD and paying the cost because they could not tolerate the failure risk. And when async SMD was available, they went that route. So I've got numbers for each of them that I'll talk about. These are not the only successes. Frank Kine wrote about a customer in South Africa in a Watson and Walker publication. And there are other customers that I know about and have talked with. But the ones I'm talking about here are ones that have shared either their charts or data from which I've made my charts. And that's why they're here. But there are other successful implementations as well. So let's start with the European bank. The European bank has two sites. They're between 2 and 3 kilometers apart. It's not that the sites move, it's that there are different cable runs. So one cable run is about 2 kilometers long, the other cable run is about 3 kilometers long. And they had deployed system managed duplexing, that is synchronous SMD, but the cost of doing so was overwhelming on the first workday of each month when all of the bank balances changed and people were checking and taking out money and all of this. So they actually turned off synchronous SMD on the first day of each month. Now, they gave me reports, which I squeezed into a spreadsheet to try and produce a chart. And I had the hardest time making it look like days of the month. So unfortunately, the way my chart boiled down, the number 9 here is actually the first day of the month, and the bars on either side are days, not hours. Now you can see that when we do have simplex activity that first day of the month, the request rate for the local system, that was the darker orange bar, is down in the 5 microsecond range, right? Because at the time, that would be a good sync request rate. And then the more yellow of the two lines represents the remote system coming to this to the primary lock structure, or in this case, the simplex lock structure, and it's getting in the order of 40 microseconds. That's because it's 2 or 3 kilometers away. The blue and gray bars indicate the number of lock requests. So you can see that the number of lock requests tend to start peaking around the first day of the month. But in general, they're doing okay. They're getting pretty consistent behavior other than the first day of the month, and then it behaves like simplex. When async duplexing became available, they now use it every day of the month. So if you didn't look at the number of requests in the gray and blue bars, you wouldn't know from looking at the yellow and orange lines which day was the first day of the month, right? Because we're getting pretty standard. The one that's local is getting 5 microseconds. Again, this was the earliest set of data I have, and at the time, 5 microseconds was excellent. And then the remote one is getting between 35 and 40 mics. So it dropped a little bit from what it had before, and they're very happy with it, and they're running happily. So the next example I have is the North American Bank. I've got 2 slides for this to look at 2 of their LPARs. So again, they had a 2 KEK, 2 ICF configuration. So they were exposed to the double failure scenario, and no matter how much we talked to them about it and about synchronously duplexing their lock structure, they tested it, they saw how expensive it was, and they said, we're not doing that. So here we are before they implement Async SMD. And so the service time is that blue line, which is approximately 3 microseconds, right? This was far more recent. This was in 2019, so they have a newer configuration with faster resources. And then the orange bar is CF utilization, and the gray bar is the sum of requests. So this is from their primary LPAR, and after they go to Async SMD, we can see that the number of requests drops a little bit. I think this was related to workload between those 2 days. The blue line for the sync service time did creep up. It crept closer to 4 microseconds, but it's still below 4 microseconds. And CF busy did go up noticeably, which is what we expect, right? CF is doing more work with Async SMD. But it's still not an alarming number, right? It peaks at about 11% busy. If we go look at their secondary LPAR, right, it's going to have very similar view of the world. And again, it's still seeing less than 4 microsecond synchronous service times, right? And again, because the CFs are the CFs, we're going to see the same thing for CF busy. And the requests have gone down on their secondary. Let's go look at the third one. I have 3 charts for this because there are some additional comparisons I can make. Again, in all ICF configuration, they had used synchronous SMD and tolerated the high service time and just paid the price, right? And so let's look at that high service time. So here we have the 2 lock structures. I'm using the RMF coupling facility spreadsheet reporter. And so one of them is the primary on top. The one on the bottom is the secondary. But again, they're not primary and secondary. They're synchronous SMD. So they're both in sync all the time. And we can see that the number of requests, the blue bars, are identical because every request goes to every structure. And the pink line, which is sync service time, is very similar. There are slight changes, and that's mostly about what else is going on in the coupling facility environment where those structures are running. Now, this chart is showing the synchronous requests. That is, synchronous from the point of view of the host CP going to the coupling facility. And those sync service times in both of these cases are almost identical. They're much higher than what I would have expected, say 5 mics in their original configuration and below 5 mics later, based on how their particular configuration is set up. And the overall number of requests, the height of those blue bars, if you will, is about 26 million requests per 15-minute RMF interval. The next chart I have is the same situation. It's still synchronous SMD, but now I'm looking at the asynchronous requests to the coupling facility. We're still doing synchronous system managed duplexing, but XCS is converting a large number of requests to a lock structure to asynchronous requests so that the host CP can be dispatched to do other work. So for these asynchronous requests, again, the service times are almost identical, right? Those pink lines have almost exactly the same shape. And the blue bars are, of course, the same shape because anything that gets converted to async is going to both of the structure instances. But the thing to notice is that 86 million requests per RMF interval were converted to async. right? So that's over 3 times. So over 75% of lock requests are getting converted to async because of how long system managed duplexing takes. Now, this customer implements async SMD, and now we're going to take one of the days for which I have data, and we're going to look at the top one is the primary structure and the bottom one is the secondary structure. So the number of requests are vastly different, right? Because all of the requests go to the top one and only the queries go to the lower one. And if you look at the scale for the left-hand axis, right, you'll see there's way more zeros on top. There was negligible async requests because almost nothing got converted from synchronous to asynchronous. And then if we look at the service times on top, you can see that we're peaking at a little over 6 microseconds, which is a whole lot better than the numbers we were seeing on the prior charts. And again, for the secondary structure, we're seeing variations up to a little over 35 microseconds for those query requests, but there's far, far fewer of them. Now, as it turns out, this particular day, I had 15 million sync requests per 15-minute RMF interval versus a total of 86 million or whatever it was, right? So their workload is different at this particular time. But what's really important here is the CF synchronous service times and how different those are. So wild success, this customer is ecstatic. And so now the question for you, are you running a situation where you should be doing system managed duplexing of your lock structure, right? If you're in that situation and you are, maybe you should consider doing async SMD. If you're in that situation and you're not duplexing your lock structure and you're at risk of one of the double failures, maybe you want to look at that. If you are a candidate, let me know. Let's talk about this because I know personally of a number of customer environments that should be doing async SMD because they're either not protected from the double failure or they're paying the price for synchronous SMD. So quick summary before we get to questions. Async coupling facility duplexing gives you robust failure recovery, simplex-like response times, even at distance. And if you're interested in deploying this, let me know. I'd love to work with you. And please consider sharing your data. I will anonymize it in ways similar to here, so no one will know who you are. But it would be great to get the word out about how well this works. Some acknowledgements. Mark Brooks, XCS development or XCF development in Poughkeepsie is very helpful in putting this material together. Some of the charts will look very familiar to you if you see his presentations. Frank Kine with his article about the bank in South Africa and other conversations and his suggestions on the terminology. And of course, Dave Sermon, who's been helpful to me throughout my journey with parallel sysplex and data sharing. Okay, let's have some Q&A. There is one question that I see in the chat. If you have the DB2s on separate CECs from the CFs, then is there really any benefit from duplexing lock one? A single failure would lose either DB2 or CF and lock one. I guess double failure CF and CEC with a DB2 on would kill the group. Okay, so yes, it's the clarification. Where are we at risk? And where does it really make sense to duplex the lock structure and the SCA? And where we want to duplex the lock structure and the SCA is where we have DB2 and an IRLM on the same physical machine with the lock structure and or SCA that DB2 and IRLM are using. If they're on the same physical footprint and there's a risk of losing a footprint, and yes, I know they rarely fail, but things do happen, right? People do make mistakes. Forklifts do drive through walls and nail systems, right? Not frequently, not often, but things do sometimes happen. And to be protected from that, if you have a situation where your DB2s are on the same physical footprint as the lock and the SCA, then you really should be duplexing the lock and the SCA. But if the lock and the SCA are on a separate footprint, I didn't give you the example where you had 3 CECs, right? And you had a DB2 on the one on the left and a DB2 on the one on the right, and you had your lock and the SCA and the CEC in the middle, right? And we can do that for production, and then we just mix and match. For QA, we have the 2 DB2s left and center and the lock and the SCA on the right. And for the sandbox, we have the lock and the SCA on the left and the two DB2s center and right. So you can mix and match with 3 KEX with 3 ICFs, as long as for a particular data sharing group, the lock and the SCA are independent of your DB2 and IRLM. So Marcus, I don't know how we do this if other people have questions, either about the CFs themselves and async and sync duplexing, or about the customer data.
Well, they could either email me or yourself, and I would pass them on to you if they email me.
Oh, I'm sorry. I meant specifically right now in the few
Oh,
minutes
right.
we have
Okay.
left.
So if anybody has
Absolutely.
any questions that they want to ask, please raise your hand on Zoom and I will unmute you.
And while we're waiting, make sure you fill in your session feedback. I know I'll appreciate the value, anything you put in here, especially comments. And don't forget to become a member of GSE UK. And I think somewhere I had my email address. Maybe that's on the cover page. Nope, it's somewhere. Well, maybe I forgot to put it on here. It's mrader@us.ibm.com. Or you can pass the questions through Marcus, and so he gets a copy of them too. That would be great. But yes, if you have any questions, let me know. I've always been a big proponent of parallel sysplex and data sharing, and this has rapidly become my favorite subtopic.
Well, this has been a brilliant session. Thank you very much, Mark. Technical, practical, and very informative. Thank you very much for your presentation, for doing this for us. And as we said, please fill in your feedback forms. It helps us to deliver good and good content for the future. So thank you very much. I shall wrap this up and we'll speak soon.
Thanks, everyone.
Thanks, Mark.